Okay, guys. Didn't get a chance to put anything up this weekend. Still, still recovering, and my energy levels are pretty low, but we're back to it now. So let's just say your star test. Um, that'll be Friday. Okay. So at the end of the week. So we left off with the sun-sized stars ending at the white dwarf and then eventually cooling down to the black dwarf. The massive stars, they essentially follow the same process, right? The beginning, they just start from a larger cloud of gas. The contraction is much quicker. They become a main sequence star much more quickly, and larger stars fuse at a higher temperature. They fuse their fuel generally quicker, so they don't last as long either. But they're gonna end up on the main sequence. That part's just the same, just a larger star. So if we had our, a Hertzsprung-Russell diagram, right? And it looks like I'm backwards here. So this way, okay? So that was the main sequence. They'd be further up along here, right? Larger and hotter stars generally. So let's move me down here. Where can I hang out? I'll hang out here. So high mass stars burn their fuel at a much faster rate than smaller stars, resulting in a very fast evolutionary pathway. So they go through their life cycle much more quickly. They'll spend less time on the main sequence and less time in the post main sequence phases, like red giants and whatnot. All evolutionary changes happen much more rapidly for high mass stars because their higher mass and gravity generates more heat. This speeds up all phases. The evolutionary pathway of high mass stars and low mass stars is the same, right? For the beginning, right? But once they leave the main sequence, it starts to change. So large mass stars share a common evolutionary pathway to small mass stars, but they diverge once the hydrogen is used up in the core and the star leaves the main sequence. Move me up here. Stars with masses similar to the sun ascend to the giant branch almost vertically. There's a little bit of whoop, right? They go almost vertically. Larger stars move roughly horizontally along the HR diagram into the red supergiant phase. Okay? So we see helium ignition, and then they start moving this way. Okay? They start going this way, then back. Right? So actually, let me simplify this. Here we have a star that has the same solar mass as our sun, right? And it goes up into the red giant phase, and then you have the helium flash and so on. This star here, 4 times the mass of our sun, right? It's already a giant star, but when it goes in towards helium ignition, it goes it's moving this way across the Hertzsprung-Russell diagram. Right? It becomes a red giant, starts cooling down, okay, but it's already really big, so its luminosity isn't changing as much as a smaller stars did. Right? And then after helium ignition, right, it starts to get hotter, right? It's getting hotter and hotter, starts fusing carbon, and then cooling down and going back, right? So larger stars move roughly horizontally along the HR diagram into the red supergiant region, and they also have a helium flash. Very large stars, I should have very in here, do not experience the helium flash, right, as they transition into a red giant. Right here, this star, 15 times the mass of our sun, as it enters the red giant phase, starts. Whoa, where'd my mouse go? starts fueling helium, then carbon, then oxygen, right? It starts, you know, it's still super luminous, but it gets cooler and cooler. So stars 2.5 times more massive than the sun. That number is not really quite correct. Okay, but it's a generalization. It doesn't always hold true. Big stars, they don't have a helium flash. Okay, so they don't become degenerate, right? If you remember, that helium core got super super hot, right? It got degenerate, and um, it caused just in terms of quantum physics, the helium to behave differently, right, and get that a massive increase in heat, right, and we'd get the helium flash. Larger stars don't tend to do that. But again, don't stress yourself up. Sorry, guys, I'm just tired. Don't stress yourself out about the helium flash, though. In more massive stars, the core density is lower when the temperature reaches 10 to the 8 Kelvin, so the temperature for helium fusion. So their core is less dense. Okay, so there's less electron degeneracy. So in the original sun-sized star, when we had the electron degeneracy happen, right, that helium core didn't expand with heat. It didn't behave normally as normal physics would demand. That core didn't expand normally, so when it expanded, it kind of dispersed heat. But in that sun-sized star, that helium core hit electron degeneracy, and it didn't for that brief period it didn't expand with heat. So if we expand with heat, we have a balance between getting hot, and that expansion kind of bleeds off some of that energy. During the helium flash, that core didn't expand, it didn't bleed off that energy, it just got hotter and hotter and hotter, and we had the helium flash. Larger stars, because the core is lower density, okay, because the density isn't as tight in a smaller star, we don't have as much electron degeneracy. So that core is able to expand, right? As it gets hot, that core can expand and start to cool, so it prevents that runaway helium fusion. Stars that are 8 times our solar mass, stars below this threshold do not reach the 6 million Kelvin needed to fuse carbon. Okay. So stars below 8 times our sun, they don't get hot enough, they can't fuse carbon, and they end as a carbon, and maybe with a little bit of fusion of carbon around the core, giving some oxygen, like we mentioned before. Or they may form neon and oxygen, a white dwarf star. It, it might be helpful if you're looking at a periodic table while you're thinking about this. But white dwarf stars are mostly carbon. They can fuse a little bit of oxygen towards their end as they get pretty hot. Right? Larger white dwarfs, they might fuse that carbon into some neon, right? But the star itself generally can't fuse beyond carbon. Higher mass stars can fuse carbon. Right? There's so much mass, there's so much gravity pulling in, they can get so hot, they can fuse that carbon into heavier elements. So the carbon will then fuse into something else, and then the star will collapse and pull more and pull more and pull more, and fuse heavier and heavier elements. So high mass stars can fuse carbon and heavier elements as its core continues to contract and its central temperature continues to rise. So remember, we got to carbon, nuclear fusion stopped, the core collapses due to gravity, gets super hot, and starts fusing carbon into heavier elements. As each element is burned to depletion at the core contracts and heats up, right? So the gravity, as fusion stops, there's no outward pressure. The core collapses with gravity, gets hotter and hotter. Fusion starts again. You then have a balance between the outward and inward pressures, right? And you start fusing heavier elements at the core. So you create layers of shells. Remember in this regular star, we had the helium, the hydrogen core, right? And then it's fused all the hydrogen into helium. Then the helium started to collapse, and we had hydrogen burning around the edge. You're getting layers and layers of elements. So the fusion of heavy elements. The ash of each burning stage becomes the fuel for the next stage. So when hydrogen is completely fused, we have a core of helium. It collapses due to gravity, gets hot, then it starts fusing carbon. Then the fusion so the hydrogen becomes helium, the helium fuses into carbon. It's not hot enough to fuse carbon, the core collapses, gets hot, carbon fuses into oxygen. The oxygen core collapses, gets hot, oxygen fuses neon, then magnesium, then sulfur and iron. So each layer getting towards the core is hotter and hotter. Okay, so if we look at this diagram, right, we've got iron at the core, right? Then we move to silicon, magnesium, neon, oxygen, carbon, and helium. You have all these different shells inside. So hydrogen burning along nicely, fusing into helium. All the hydrogen is gone. The helium remains. It's not hot enough to keep burning. The helium core contracts due to gravity, gets hot enough to start fusing helium. So then we have balance again. The helium gets all consumed. You're left with carbon, right? It collapses because you can't fuse carbon, it's not hot enough. As it collapses, it gets hot, starts fusing into oxygen, right? When only oxygen remains, the core collapses due to gravity, gets super hot, enough to fuse oxygen into neon, and so on. So each core gets hotter and hotter and hotter and hotter. And each core that gets hotter and hotter starts going through their fusion process faster and faster and faster. And you're going to have these shells, right? These shells burning along. It's worthwhile noting as well, outside of the core, you've got your non-burning hydrogen. So when we say burning, it's not going through fusion, right? It's just super hot due to the core of the star, but it's not hot enough to fuse. Where can I move here? Can I shrink me down? Let's just go down here. Okay, the next point is very important. Nuclear fusion stops at iron. Oops, where'd that go? Okay, sorry, I'll be with you in just a moment. Okay, sorry, I'm back. So, contraction, reignite, contract, reignite, contract, reignite. And it stops at iron. Nuclear fusion stops at iron. Okay, and it's kind of interesting why. No core can fuse past iron. That doesn't happen. So, fusing hydrogen into helium creates particles with less mass. So, hydrogen can be fused into deuterium and then into lithium. But if we look at this graph, right, it says mass per nuclear particle, right? Hydrogen to deuterium to helium, the mass decreases, right? We go up to lithium, mass increases again, but then it starts to decrease to carbon, to oxygen, and then to iron. So we see mass dropping, and this relates to E equals mc squared. Okay. So fusing hydrogen into helium creates particles with less mass. Okay. So if mass and energy are equal, if you lose mass, it means you have more energy. This is the energy being radiated out. So fusing hydrogen into helium creates particles with less mass. Mass is lost, therefore energy is lost, is released. So that mass that was lost, if you lose mass, because they're equal, right, you've lost energy. That energy is radiated out. As elements fuse, they keep releasing energy. The starlight we see, up until iron. Once we reach iron, if you were to try and fuse iron into heavier elements, so after iron, combining nuclei, so nuclear fusion, increases the mass. So if we were to take iron and fuse it, so if we were to take two atoms of iron and fuse it, okay, the resulting molecule becomes heavier. Okay, the resulting nucleus gets heavier. So after combining nuclei, right, which is fusion, increases the mass. Therefore, it absorbs energy instead of releasing it. So at this point during fusion, right, we can't go past iron because it is now absorbing energy. It's not releasing energy like a star would. So at that point, right, the star is no longer giving off light. So once iron forms in the core can no longer emit energy, right? Because if we were to fuse iron into the next element, right, it would absorb energy. It's not releasing energy. It's not releasing light. The star is done, right? The star is no longer giving off energy. So once the iron forms in the core can no longer emit energy and the core can never reignite. The star is done. So there's no longer fusion happening here, right? So if there's no fusion, there's no energy pushing outwards. So the iron core will start to collapse. Okay? So once the iron forms in the core can no longer emit energy and the core can never reignite. Outward pressure from nuclear fusion stops. Nuclear fusion's done, there's no more outward pressure. Okay? And we get the collapse of the core. The iron core, boom, gravity pulls it in. And there's so much gravity. It's so huge and so dense. Like this gravity would just rip your body apart into its constituent materials. So this collapse, right? This big giant ball of iron collapses, right? And the core gets super hot. So we go to 10 billion Kelvin. Or the star starts burning at 15 million, right? Now we're up to 10 billion. Right? So we're at 10 billion Kelvin. So we're so hot, right? We're so incredibly hot. So the collapse causes the core to heat up to 10 billion Kelvin, where photons of radiation, so the core, it's so hot, it's glowing super hot, right? The radiation that's coming off of it, and this radiation isn't due to nuclear fusion, this is due to heat. Okay? So the photons of radiation have enough energy to break the nuclei. So there's so much energy being released from this heat that the iron nuclei, the iron atoms, are broken apart into their basic constituents, the protons and the neutrons. So in essence, nuclear fusion, all that fusion that's happened is undone. We don't have an atom anymore. Atoms are gone. We now have subatomic particles. So we call this photodisintegration, right? Photodisintegration undoes nuclear fusion. Okay? So we no longer have atoms at the core of the star, right? The iron core collapsed, became so hot, that heat was so intense it destroyed all the atoms or broke apart all the atoms that were in that iron core. So we no longer have an element at the core. We've got subatomic particles. But this point is important. Photodisintegration undoes the nuclear fusion and absorbs a lot of energy. So it absorbs a lot of that heat energy that's there. That heat was still pushing out, even though it's not nuclear fusion, that heat is still pushing outwards. But this process cools the core even more, right? So there's less outward push. The core is going to collapse even faster, right? This cools the core even more, reducing thermal pressure, which pushes out, and that accelerates the collapse of the core. So the core just keeps collapsing. The core is entirely electrons, protons, neutrons, and photons, right? So subatomic particles and the particle of energy, but extraordinarily dense, right? And this density is crushing everything together, right? So the density crushes photons, so energy particles, with electrons together, forming neutrons and neutrinos. So the electrons get used up. Right? Photons and electrons create neutrons and neutrinos. This is important. There's no more electrons. If you remember, electron pressure stopped the cores in the sun-sized stars from collapsing and stopped, the white dwarf from collapsing completely. Okay? So this electron pressure, right, stops the collapse complete. Right? But because there's no more electrons, there's no electron pressure to, the negative and negative repelling each other. That stops, right? There's no pressure to support the core, so the core collapses even further. So this leads to the supernova explosion. So the core collapses to the points where the neutrons that are left, right? The neutrons, that matter, all comes into contact with each other. Right? But we can't compress it any further, right? We can't reach that compression any further. We've compressed it as much as it can. So the neutrons resist further compression as the core continues to get more dense. So there's more and more matter squeezing, more gravity, squeezing, but it can only squeeze so far at this mass. Okay? So the neutron, so that whatever's left is just neutrons. It's kind of like an elastic. You put so much pressure on it, you squeeze it so much, it rebounds outwards explosively, right? And as it rebounds outwards, it explodes the star in a type 2 supernova. Right? It's worth noting that all this stuff we've talked about, that happens in less than a second. Once the core starts its collapse to rebound, that's less than a second. It's super fast. Okay, once we've hit iron and the core begins its descent, right? Super quick. So that rebound creates a huge shock wave that explodes outwards, rips apart the outer layer of the star, the non-burning layer, right? And then we also have those shells of all the other elements, right? So all those element shells and the non-burning layers of the star, they explode outwards. So this hurls heavy elements into space, right? And hurls all these particles away, right? That can be used to build new stars, right? Or all those elements, the carbon, right? The neon, the oxygen, the magnesium, the silicon. Those are the elements we find, in our soil, in our rocks, in our bodies. All those elements that make up you and that make up our earth, right? And the things around you. Look around you. All those things are made up of elements. They were all created by the destruction of big, massive stars. So an extremely powerful shock wave results in exploding the outer envelope of the star, This material that's shed includes the heavy elements in the shells, and those are hurled into outer space. Right? We call this a core collapse supernova or a type 2. Right? And when this star explodes, its brightness will exceed that of a galaxy. Right? When they occur, right, we can see type 2 supernova. I think there was one in the 80s. It was in the southern hemisphere that was visible, that people could see it for several days, right? Even in daylight, there was a spot in the sky that appeared that was extremely bright. Let me see if I can find it here. Supernova. I'm just going into Google here on another channel. On another tab. Supernova visible from Earth. Images. No, it was quite a while ago. I'm gonna have to hunt for it. And okay, the next type of supernova, and we're kind of taking a tangent here, right? The next type of supernova is a type 1 supernova. Okay, and that's what happens. So we're going kind of jumping back to a white dwarf. So we're not talking about giant stars right now. We're talking about white dwarfs again. Okay, so we're going back to a sun-sized star. Right, so the type 1 supernova or the carbon detonation supernova, right? And this little image is when I googled white dwarf, they also showed me this little white dwarf here, so it made me laugh. So, if a white dwarf star, the remnants of a sun-sized star, is is orbiting and is near to another star, right? This white dwarf star may actually become or enter into a nova phase. It might explode. So white dwarf stars accrete matter, and then this matter may explode, and that would be a nova. I don't know why I'm missing text here. Okay, so a white dwarf star can, because it's got such intense gravity, it's so incredibly dense. There's so much matter compacted into a small area, right? It's going to have very strong gravity, and it can start pulling a star apart or pulling gases off a star and building up matter around around the white dwarf. So the white dwarf stars do not necessarily expel or consume all the accreted matter. The white dwarf stars may grow in mass with each nova cycle. So don't worry about that term nova cycle right now. The white dwarf star is pulling matter from another star, and it's getting more massive. It's getting bigger and bigger. So as the mass of the white dwarf grows, the required pressure to support that white dwarf star now increases. Okay, we need more pressure, right? But the white dwarf star, remember, it can't be compressed any further due to electron degenerate pressure, right? But if that white dwarf star becomes at about 1.4 solar masses, this was known as the Chandrasekhar limit. He was the physicist who first calculated this. If that white dwarf star accumulates enough mass to reach 1.4 solar masses, it reaches a threshold. Right? At this point, the white dwarf star is too massive to support, it's too massive for the electron degeneracy to keep it from collapsing. So at this point, the white dwarf star will collapse and its internal temperature will rise. So the white dwarf star, which normally wasn't collapsing, it collapses because it's become too massive. It gets hotter and hotter, and it starts to fuse carbon into heavier elements. So that white dwarf star is actually kind of reignited now. It's become a fusing star again. But that collapse causes that carbon fusion not to happen just at the core, but throughout the entirety of the white dwarf star. Right? The entire white dwarf star was a carbon core. And as it collapsed, that entire carbon white dwarf ignites. It starts fusing, it starts going through nuclear fusion everywhere, not just in the center, but everywhere all at once. So the carbon fusion occurs simultaneously throughout the entirety of the white dwarf, and the star explodes in a carbon detonation supernova or type 1. Okay? So that could be the fate of our sun when it became a white dwarf if it had another companion, if it had a star nearby that it could suck matter off of. So all high mass stars, so this isn't us, this is a big stars, will become a type 2 supernova. Okay? Only a small fraction of white dwarf stars will become a type 1 supernova. Okay? And ignore the cartoon. Okay? So massive stars collapse, start fusing heavier elements, collapse again, fuse heavier, collapse again, fuse heavier, collapse again, fuse heavier, collapse again, fuse heavier, right? Collapse again, fuse heavier, eventually till they reach carbon, right? Thing is, fusing carbon, right, doesn't release energy, right? It consumes energy. So at this point, the star can't fuse anymore, right? The carbon core collapses, right? Gets hotter and hotter, right? But it can't fuse into anything else. It becomes so hot, right? Becomes so hot that heat causes photodisintegration, breaks all the carbon nuclei up into their basic components, right? And then they collapses further. Electrons fuse with photons. They become neutrinos and neutrons. The electrons are gone. So if there's no electrons, there's no degeneracy pressure to prevent the further collapse. The core collapses even further till it compresses the neutrons as tightly as possible. Okay? Then the neutrons, because they can't be compressed any further, they explode outwards, blowing up what's left of the star in the type 2 supernova. Okay? And remember, the type 1, this probably was the best place for me to put it. The type 1 is what happens to a sun-sized star at the end if it has a stellar partner. Okay, so here we have a type 1 supernova, the white dwarf. The white dwarf scenario. Okay, so here we've got a star. Here we have a white dwarf or a star that's given off its planetary nebula. It's died. The white dwarf that remains, right? It starts pulling a nearby star apart, right? It gets heavier and heavier, becomes more massive and massive at 1.4 times the sun solar mass or the Chandrasekhar limit. That's enough to overcome electron degeneracy, right? Fuses it starts compressing the core, becomes super hot. The entire star fuses carbon all at once. The star explodes. Type 1 detonation. Right? Type 2 detonation, we fuse until we get the iron core. Fusion stops at the iron core. Collapses, collapses, collapses. Photodisintegration. Collapses, collapses, collapses. Rebound, right? And the non-burning part of the star and the heavier element shells are all blown away. Okay, and there's going to be a remnant left behind, which will be a neutron star, which we will talk about tomorrow. Okay, there's a list of questions. Right? And this topic is quite dense. Okay, this is going to take some thinking about. Right? There's a list of questions. I want you to try and answer those questions. Okay, that will be your homework tonight. Okay, whenever you see this, whether if you see this Monday or if you see it Tuesday, go through, try and answer these questions. Okay, so I'm going to end the recording here because that's the last slide. Try and answer these questions. Tomorrow we'll talk about the questions. Okay, I'll answer them for you, but try them on your own. Okay, I'm not assessing this, but I want you to try it. And then we'll talk about what happens at the core, what's left behind after the supernova.